How's everybody doing? All right. I probably don't need to record me passing the test back, but I can start talking while I do it. So I got your test, and I posted everything, so you should have everything on.
Thank you.
I don't have a thing for you, so you get scrawled. I think everybody did pretty good. I'm pretty pleased with how everybody did. I don't think I have anything else to say about the midterm right now. Let me know if you have any questions. But today we're going to go through, let's see, what do we have? We got readings and we got a numerical homework. So I'll go through the numerical homework really fast. And I mean really fast. How do you guys feel about the numerical homework? Pretty straightforward. I'm going to just open it so that we can... No, that's not right. Boop, boop, ba-doo. Okay, so the entire purpose of, well, okay, so there are basically two purposes of this assignment. The first one is just getting you to read this HDF5 file. Doesn't really matter what that is. It's just a package with stuff in it. HDF5 is a data format that lets you package data in a nice way. We don't need to know anything about it other than it's a good way to get stuff out off disk. And here's a file. It's the main sequence data file. So we downloaded this file, stick it in the same thing. Everybody seems to have done okay, I think. So this section reads the file. So you import NumPy and Matplotlib, and then you import this thing h5py, which should have been installed with your Anaconda install. I think some of you, if you didn't do it through Anaconda, had to install h5py, but it's not painful. So then it just opens this file. Oh, and it should close the file too, but I forgot to do that. But it doesn't make a huge difference. So what it does is it reads, so it opens up this HDF5 file, and then it makes this dictionary, star data, and it loops over all of the things in the file pointer. So, okay, f pointer equals hdf5.file and then a file name. F pointer is a file pointer. It's a thing that is attached to that file, and I can do things like read and write using that file pointer. So we just read, so here's where we use it again. We just read it like a dictionary. So square brackets with stuff that isn't a number inside means it's a dictionary. So that's like a collection of stuff that you can access by strings. So, and this colon actually reads it off of disk. Otherwise, you just get a pointer to the thing on the disk, which isn't useful. You need to actually read it off the disk. So we read it off the disk and we set it equal to this star data. And then we can see that it has keys, absolute bolometric magnitude, visual magnitude, B minus V, the bolometric correction, which we didn't talk about, the effective temperature, which we will talk about, the luminosity in solar units, the mass, the radius, the spectra class, the star name. So these are things there. The second one, get some stuff out of this, which I think everybody did fine. And then the third one, plot this. And I think everybody got it. Does anybody have any questions or things they want to talk about this one? Everybody all right? So there's another one which is shorter. No, longer. This one is short. The other one is a little longer. Not a ton longer, but a little longer. It uses the same star data. And this time, I want you to write a function that returns a color from a temperature. Make sense? So we want to use color, which is easy to measure, as a metric for temperature, which is hard to measure. So this is what we're going to do, and you'll see that if we just use a simple black body, we can get that. The other thing that the next section talks about are filters. Actually, since it's due tomorrow, I'm going to real quick just run through homework 4. Because it's up. So again, we have this. So the homework starts off with these units and the star data. So it's the same stuff, same boilerplate stuff that we've had before. And then, I forgot about to talk about this. Okay, so what we want to do is with this homework set. This is why I pulled it up, because there's things that I want to talk about. What we're doing is playing with filters in this. So we're going to take a black body, and we're going to filter the black body based on spectral filters, based on color filters. And then we'll use the color we get from filtering the black body. So we start with a black body. Second, we'll define some filters. Then we'll get the color from the filters. So the black body, so temperature goes in. Temperature gives you a black body. That's it. That's the only knob on a black body is the temperature. That defines the curve completely. So you define the black. So you start with the temperature. You define a black body. We define the filters, and we take two filters. We'll do B and V, and then we get a color out of it, which is some number. And then we'll plot it and we'll compare. So the first thing we need to talk about is how do you actually do an integral? And I do this in a little bit complicated manner because that's the way I think about the things. That's the best answer I got. When I do an integral, I've got some function f of x dx. What's an integral? It's the area under a curve. It's a sum. It's adding a bunch of stuff up. Right? So I can think about this as this is the limit as delta x goes to 0 of f of x times delta x, and it's the sum on all those things, delta xi, xi. So I take my function and I break it into little chunks, and I just add up the area under the curve in each one of these little chunks just by base times height. Right? This is the trapezoid rule. There are fancier ways to fake an integral, but this is the easiest one. So as I send the size of my partition to 0, I recover this integral. Now on the computer I can't do that because that requires an infinite amount of memory, and I don't have an infinite amount of memory. So we just get rid of that limit, and now my integral is just the sum on some function times the width of the bin. So what we're going to do is we'll make an array of wavelengths, which is our delta x, and then we need to know what the delta is. So sorry, one second. Let me. So the first thing we do is we take the difference of these two arrays. Let's slide this up this way real quick. So I'm going to have an array of wavelengths. We'll call them lambda. Okay. And I need to know what delta lambda is too. So I have, actually let's call it something that I can actually type. Let's call it L. L is for wavelength. So L is going to be some kind of array of numbers. We like to use linspace for this because it gives us all the numbers between A and B. Now what's delta L? Delta L is, so L is an array, so I want to take this one minus this one for every element, right? So I'm going to do this in a funny way. When I have an array, I can say L of 0, that gives me the 0th element, right? If I say L of 0 to 7, what does that give me? It gives me everything from 0 to 6, including 6, but not 7. Because arrays start at 0, and so you don't need to count everything. So this gives me all the elements from L from 0 to 6. L of 1 gives me everything but the first element. L of minus 1, colon minus 1. So blank defaults to the end of the array, so I don't have to keep track. So this is 1 to the end. This is the beginning to minus 1, and minus 1 is the last element. It starts counting from the other side. This is a very nice feature of Python. Not all programming languages do this. But if you need to get the back element of an array, minus 1 is a good way to do it. So if I take L starting at 1, and I subtract L starting at 0, I'm left with delta L along my on my array. So if L is 0, 1, 2, 3, 4, 5, 6, then this expression, L from 1, is going to give me, let's say we just go up to 6, this is going to give me 1, 2, 3, 4, 5, 6. And L going from 0 and going to the end is going to give me 0, 1, 2, 3, 4, 5. And then I take the difference of these two arrays, and I'm left with 1, 1, 1, 1, 1, 1, 1. Which is kind of dumb, but if I had something that's more complicated, then I get the right answer for free. Yeah?
Why does the negative one give you 0 to 5?
Because this takes me from the beginning of the array to the end, but you skip the last one.
Oh, okay.
Does that make sense?
Yeah.
This one is you start at the first and you go to the end. So the reason that we need to do this is because this is a little bit complicated, but I figure I'll throw it out because it's a super useful tool. I do this when I'm asking questions of data all the time. So we're going to define a function, a function that's a function of lambda that's a Gaussian, and it needs to be normalized so that it works like a filter. And all of this is described in the text. So then if we want to integrate my black body times my Gaussian, so I'm going to make a Gaussian that's a function, and it's going to make an array that looks like a Gaussian. So I'll make two of those, one for B and one for V. I'll make a black body. I'll multiply the black body by the filter to get the B flux. Multiply the black body by the other filter to get the V flux. Then I take those fluxes and I make a color with the thing that looks like distance modulus. Does that make sense? It'll make more sense or less sense. Office hours tomorrow at 4, so that we can go over all this. Let's see, is there anything else that I want to go through? Yeah, so this is just playing with numerical integration a little bit. So we do an integral, and then we integrate the black body. All we do, I'm sorry, I forgot how I did this assignment. All we do in this function is, in this assignment, is find the color of the sun, assuming it's a black body with a certain temperature, and then compare. So we just assume that the sun is a black body, and we see if we get the right color, and you should. But we use this kind of complicated machinery, and it might feel like kind of a way more complicated than it needs to be, but it's tools that are going to be useful for even more complicated things than this. So once you can't do the math by hand anymore, then you have to use numerical integration. Okay, this will make more sense once you start doing it. Now let's go through. How am I? All right. Some questions. Let's make them bigger so I can read them. Okay, this symbol, M with a real big black dot. I cannot figure out how to get that symbol in LaTeX because I can't sort it out. But anyway, so M with a big black dot means black hole mass. And it doesn't mean anything. It's not anything as specific as and sun. This is 2 times 10 to the 30 grams. This is just whatever that black hole is. So it's just a decorator. What's the purpose of that angle theta BH? So that angle, I'm going to answer the question real fast. But this angle theta BH is about what angular resolution do I need? So how close do I have to be able to see a black hole inside a galaxy? So this theta BH, this is if I'm looking at my velocity dispersion, and my velocity dispersion does something like that. My black hole does something like this, where it gets really high, really close to the center, like 1 over r. So theta BH is how close do I need to see my galaxy to be able to see the effects of the black hole, the stars orbiting the black hole. So theta BH is the angular resolution necessary to separate stars around the black hole from the bulge. So I've got all of these stars that are rattling around the bulge. They've got some velocity dispersion. Velocity dispersion near the black hole gets really, really high when you get really close to the black hole. That's what we want to see. So we need to get close enough to see where it gets really, really high. Does that make sense? What makes a galactic nucleus active? It's the accretion from the black hole. So the black hole has to be feeding on things. And if there's stuff, it will feed. So having gas in the environment around the black hole makes it active. I will explain synchrotron. A couple of you were confused about synchrotron, and I'll go through that. How do jets tell us about the internal structure of a quasar? It's a super good question. I'll talk about jets in a little bit, but the basic idea of a jet is you get all these magnetic fields, and magnetic fields are kind of like rubber bands in a fluid. So as the disk of the black hole, it's spinning like crazy, it wraps up those magnetic fields into a tangled mess. And that tangled mess kind of grows kind of like I don't know, like a loom or something, or like knitting. Like you ever watch somebody knit a scarf? It's kind of like that. It gets all tangled up and then it kind of shoots out. It's kind of like, also, if I have a stick with a donut on it and I fling it really hard, I can make that donut go really fast, right? Or if you've ever seen the game Jai-Alai, Jai-Alai is a similar thing. You get a really long lever and you get a little ball that's on that lever, and you can whip it really fast because the stick acts as a lever arm. In the jet around a black hole, the magnetic fields act like a lever arm as well. I'll go through this again on Thursday. So the magnetic fields act like a screw, and they shoot stuff out from real close to the center of the black hole out 500,000 light years. So it allows us to see what kinds of things are going on in there indirectly. Let's see. How often are quasars seen? They're all over the place. So I don't know what the fraction of galaxies that are active are, but it's a substantial fraction of galaxies are active. All galaxies that are large have a black hole. I'm pretty comfortable saying that. I don't know of any massive galaxies that... So there are little tiny galaxies like the LMC and the SMC and all these dwarf things. They may or may not have black holes in them. They don't have million solar mass black holes, probably. But I don't know... but bigger galaxies have bigger black holes. So quasars are everywhere. Black holes are really everywhere. Why does the book only suggest that one side of the quasar has a jet? This is because of beaming. So several of you asked about beaming, so I'm going to talk about that real quick. If I got a truck, and I'm on the back of this truck, and I'm throwing footballs in every possible direction, right? So footballs come out in every direction. Now, if the truck is moving slow compared to how fast I'm throwing out the footballs will again come out in every direction. But if the truck is then moving quickly with how quick I am throwing the footballs, say I throw the footballs at 10 meters a second and the truck is driving at 9 meters a second, then all of my velocities are going to be in that direction, right? So if I'm standing behind the truck, I'm not going to get hit by very many footballs because they're all going in that direction. Does that make sense? This is a really dumb analogy. This is how beaming works. So if I have an object, I'm going to just change my football analogy to now a blob of gas that's radiating photons. If the blob of gas is moving fast compared to the speed of the photons, so that means it's relativistic. So if it's moving relativistically, most of the photons come out in that direction. So if I'm over here, the blob of gas looks twice as bright as it would be if it was holding still because I get all of the photons. Whereas if I'm over here, it looks half as bright as it should be because they're all going in the opposite direction. So this is called Doppler beaming. So since these jets come out at a fair fraction of the speed of light, when I'm looking at a galaxy, it's got a jet that's coming at me and one that's going away from me. The one that's going away from me I can't see as well. Let's see. Why are QSO's spectrum broad in the UV and optical? I will talk about that today. It's because they're a sum of black bodies. Trouble grasping what a QSO is. So a QSO is a really bright thing. So there's a couple of ways that you could say what a QSO is. So a QSO is really an observational definition. So it's a thing we see in the sky that is way brighter than a star. That's it. Now you can talk about what the actual physical mechanism is. That's a black hole that's accreting like crazy, and because it's accreting, it gets really, really hot. Because it's really hot, it's really bright. We'll go through those details too. Let's see. Do all galaxies contain a supermassive black hole? All massive galaxies do. So the mass of the galaxy, the mass of the black hole goes like the fourth power of the velocity dispersion of the galaxy, which kind of goes like the mass, or maybe the mass squared, depending on what kind of galaxy it is. So bigger things have bigger black holes. I thought AGNs were all black holes. Yes, that's accurate. Are there differences? Are there different types of AGN that influence galaxies different? Yes. So AGN get grouped into a two parameter family of things, and we can kind of describe any one of these AGN as in this paradigm of two parameters. And the parameters are how aggressively it's accreting. That means how much stuff is nearby. And how you're looking at it. That means, is there crack blocking your view? So things that are accreting more aggressively are going to be dumping a lot more photons into the galaxy. So they're going to suppress all the star formation in that galaxy. It's going to really wreck the galaxy. So there are different types of AGN, and they affect the galaxy by the way of their accretion rate. What's the difference between an active galaxy and a regular galaxy? Regular galaxy doesn't have a black hole that's feeding. So our galaxy is not active because there's not enough stuff around the black hole. What are lobes? I'll show you a picture of lobes. When I take a radio image So these galaxies are blowing jets. So there are these FR galaxies I don't remember their names. So I got some galaxy. Here's just the center of the galaxy. It's got a jet. That jet is blowing stuff, right? So that jet blows stuff out and it fills up a cavity. These are the lobes. Sometimes the lobes are detached like this. Sometimes they just kind of come off and they're attached like that. Sometimes they're shot out a long way before they start to run into the medium. What do you think, given our two-parameter family? What do you think the difference is between one of these things that has close-in lobes versus one that's got lobes that are far out? What do you think the big difference is between the AGN? So remember, the two parameters are how aggressively it's feeding and how I'm looking at it. So which of those two parameters is going to matter for how far out these jets can go?
How
Aggressively it's feeding. More feeding means more energy output, which means the jets can go a lot further. So when I've got a really aggressively accreting black hole, it can shoot these jets out really far before they get stalled. So why does it make a blob? Because I'm sure I've got a good physical sorry, all of the analogies that are coming to mind are really not particularly useful. So basically, I've got a jet of stuff, and it's moving through other stuff. Space isn't empty, right? Space is filled with gas. Maybe that gas is real low density, but then I have a whole crap load of it, so there's gas. So when I have a jet that's moving into this cloud, it's going to mix with the cloud and it'll become turbulent. And this mixing and the turbulence makes it not a jet anymore. So the jet is straight, and the mixing and the turbulence makes it some round, fluffy thing. So the longer it can stay straight, the further it can go before it gets entrained.
So wouldn't it also be like when the lobes are like attached to the black hole? It's just there's more stuff close to the black hole. Not, or I guess it also correlates with it eating more too.
Yeah, that's right.
So
well, the lobe is far away. So this is the galaxy, and this is like 25 kiloparsecs. So this is like 100 kiloparsecs. So this is a really large distance. So you're not directly seeing the feeding, you're just seeing the belching after the feeding.
I was mainly referring to like the part where like the red lobe kind of just expands immediately or seemingly immediately, and the other one can go further, so that's just there's more stuff closer. Right?
Yeah, this one has more stuff closer to the galaxy. Let's see. What would cause an SMBH to be a QSO versus a liner versus an optically violent variable? This is how they're feeding. So the way in which the thing is feeding mostly. So let's see. So all galaxies with a bulge have a black hole in the center of the bulge? Yeah, I think so. Why do quasars have strong radio emission? Is it just redshifted UV, or is it physics? So this is a good question. The radio is physics. You got to be redshifted really substantially to redshift UV into the radio. I don't think we can see anything that far away. This comes from synchrotron radiation and magnetic fields, and I'll talk all about where the radio emission comes from. But basically, I got a magnetic field. Magnetic fields are blue. My electron, if I've got a magnetic field here and I've got an electron, that electron's going to go in a spiral around that magnetic field, right? It can travel this way, but it's got to go in a circle this way. Since I got an electron that's moving, that's going to radiate. The frequency of its radiation is the frequency of its rotation. So as it rotates around at radio frequencies, it gives off radio photons. And these are polarized, which is useful. I don't have any pictures of that this time. I probably should. What are radio lobes? I just answered that. Oh, and are the radio jets, so where's the radio coming from? The radio is coming from the electrons that are kind of all along the jet. That was reading 1. Reading 2. What is photoelectric absorption? So that's just the absorption of a photon. I forget the context now that was in the book. But, oh no, it was in Thomson's scattering. So when I have an electron and a photon, that photon can either absorb that electron can absorb the photon and just take all its energy, which is completely inelastic scattering, or the photon can completely elastically scatter off, and you have Thomson scattering. So Thomson scattering is elastic scattering. Absorption is then inelastic scattering. And I apologize for the microlensing section. I forgot to tell you not to read the microlensing section because I forgot that it was there. I'm not covering microlensing in any of this stuff. Now you've read a little bit about microlensing. A little bit stronger now. I'm not going to cover it at all because there's just too much to cover, so I'm going to just skip all the microlensing. If you're stoked about microlensing, go back to the beginning of where they talks about it in this section. I think it's in chapter 3. But I'm not going to cover it because I can only cover so many things. What is meant by superluminal motion? What does superluminal sound like?
Faster than the speed of light.
Faster than the speed of light. So we have these jets, and I'll go through this in detail if I don't run out of time. We have these jets that you can see there's an AGN, and there's blobs of gas that are coming out of it in the jet. Now they're moving really fast, so if you take the same picture a year later, then this blob is over here, and this one's over here, and this one's over here, and this one's over here. And then if you keep going, so this is time now, in this direction, I can find out how this blob is leaving the galaxy, right? I can find its velocity, right? How do I find its velocity? I take its position and I divide by time, right? D equals distance over time, or V equals distance over time. And I get a number that's like 5 times the speed of light, because I didn't do the relativity properly, because this is only true, this is only true if it's not relativistic. If it's relativistic, you gotta do something smarter. Also, this thing moves a lot after the photons come out, which totally hides a lot of the motion. So the photons come out, and then it moves really fast and goes way the hell over there as the photons are traveling towards us because it's moving close to the speed of light. So it looks like it's way over there, even though, well, it's way over there. But it hides a lot of the motion in the travel time of the photons. So I'll go through that in detail later, too. Have you guys studied relativity in modern? Okay. So I won't feel bad going over that. What is Faraday rotation? So Faraday rotation is the rotation of a polarized signal. So if I have a quasar, sometimes the light that's coming off of that quasar is polarized. That means the electric field is all lined up. The electric field is consistent. So if I go then to, if this photon then enters a bunch of electrons, it's going this way, and I got a magnetic field that's in this direction. Let's look at this from the front. So this is now, my photon is coming at me and it's polarized in this direction. That means the electric field is in this direction. And I got a magnetic field. Oh, the magnetic field can't be this way. The magnetic field has to be this way. This magnetic field nobody cares about. This magnetic field matters. So this electric field from a photon, this is a photon, big radio photon, but it's a photon. But it has an electric field. What's an electric field do to these free electrons?
Takes it forward.
Yeah, it's going to go in which direction? Just think about what the electric field is doing. So if I've got an electric field that's in this direction, where's the electron going to go? Up. I mean, okay, maybe there's a sign error, so it'll go down. Okay, but it'll go along this electric field. Then what does the magnetic field do? Perpendicular. So the electric field from my photon is going to make my electron do this. It's going to make it go. It's going to hook in a curve. There'll be some curvature to it, but it's going to make it go to this left and right too. What does that give me? Now I have an electron that's accelerating. An accelerating electron gives me photons. More photons. These photons are in this direction. That's different. So Faraday rotation, replace. So Faraday rotation is the rotation of the polarization vector of a radio photon by magnetic fields in plasma. Now, one of the cool things about Faraday rotation is it's proportional to the wavelength. So if this wavelength is bigger, then it's going to have more time to accelerate the electron, so the shift is going to be larger. Does that make sense? Longer photon, more acceleration up and down, more acceleration left and right because of that same magnetic field. So the actual amount of rotation, so what I do is I take a radio image of a quasar, and I take a polarized image at a bunch of different wavelengths. And at one wavelength it looks like this, and another wavelength it looks like this. So I look at the shift versus the angle, and the rotation measure is proportional to the angle squared. It's a very nice relationship. And the rotation measure is also proportional to the line of sight magnetic field times the electron density along the line of sight. And it's an integral along the line of sight. So Faraday rotation, and you don't need to remember much of this, Faraday rotation is the rotation of polarized vectors from plasma. You can use it to measure the magnetic field. This is why we like it. How would magnetic fields play a role in forming jets? They do everything. Magnetic fields do everything in forming the jets. They make the jet. They work like a corkscrew to corkscrew crap out of the environment. What does it mean that the AGN has a long memory? So what it means is that AGN is stable for like 10 million years, because we can see these jets that stretch out 10 million light years. So the thing has to be stable for 10 million years. Okay, scale everything back because they're not actually going at c, they're going at a fraction of c. But we can tell that these objects, that the jets are long and large and straight. So a lot of these things say that the galaxy has to have been doing the same thing for a long time. So it's got a long memory of what's going on. I'll do Eddington luminosity in a second. Why do BL-lac objects have a nearly featureless spectrum? It comes back to this beaming idea. I've got beaming from the jet, and for a BL-lac object, the jet is pointing straight at me, so I'm seeing all of the relativistic velocity of what? Of the material in the jet. Now, that's just some hot crap that's coming at me really fast, so that's all I'm going to see because it's beamed. So I see all of those photons, and that beamed signal swamps everything else. It's like turning up the volume on just one instrument in an orchestra. So just one instrument dominates everything else. You can't hear the rest of the lines and the broad line region and the other lines. So you can't see the rest of the stuff because it's so bright, because it's beamed. What is reverb mapping? It's very cool. You flick the black hole, and then everything else dongs a little bit later, and you can tell how big the thing is. I'll go through that in detail. Why is polarized radiation non-thermal? It's a very good question. Um, uh, Thermal photons are things that come out of the random motions of the electron, of the stuff, and the random motions aren't going to give you a polarized signal, because a polarized signal is by definition all the motions in one direction. So you got to have something that isn't just the temperature in that signal. So you need something like a magnetic field or a violent explosion to give you polarization. The microlensing stuff, you can skip that. Our type 2 QSOs, oh, that doesn't say QSO, brighter, they're just brighter Sieverts. Yeah, near as I can tell, a type 2 QSO is like a really bright Sievert 2. I'll go through that in a minute. I just talked about beaming. Why are AGN classified based on inclination angle when it's not actually a property that the AGN has? It's a property that I have. So why am I classifying that thing based on how I'm doing? Because it's astronomy. So astronomy is about looking at the sky and saying, hey, I found this thing. It does this. And then when we piece them all together, we're like, oh, yeah, so this and this and this, they're all the same kind of thing, just they look different. They're all the same kind of thing. But that came like 20 years later. So all of these things were observed in the 40s, but then the picture of where they really came from didn't really come together until like the 1990s. Beaming and synchrotron and microlensing, which I'm skipping. Okay, any other questions that anybody wants to go through from the questions? Okay. Oh, okay, half hour. That's okay. I'm glad I went through all the questions. Yeah, go.
So the beam of like material, like where is that coming from? Is it coming from like the disc, or is it like something that it's like flying by and then kind of gets flung out really quickly? Like where's the beam of relativistic material coming from?
Sorry, that wasn't doing anything that I expected. So, sorry, jet looks. From the top, I have a disk, the black hole in it, and it's rotating. It is differentially rotating. It means it's rotating faster in the middle than it is in the outsides. And it's magnetized. So if I look at the side, I have a magnetic field that's like this. And so if I have a little blob of stuff that's in the atmosphere, wherever it came from, it's experiencing two things. It's experiencing the gravitational pull from the black hole. It's going to pull it down the magnetic field. But it's in a rotating system. So there's also a Coriolis effect. Omega cross V, or however Coriolis goes, or is it V cross omega? There's a Coriolis effect that's going to push it out that way. That make sense? So when this thing is whipping around, if the angle is right, then we'll have material shot out that way from the Coriolis force. And of course that's going to cause a pressure gradient, so it's going to just suck material down from the disk itself. So from the disk and the atmosphere around the disk, especially where the magnetic field is getting amplified, which is closest, the magnetic field is getting amplified, we have this corkscrew that kind of corkscrew stuff out. So as this is rotating, it wraps up this magnetic field into like a spiral and makes like an Archimedean screw. Are you familiar with the Archimedean screw? It's just a tube that's in a spiral that you can put one end in water and turn it around, and the water goes up the screw. This is the same idea. So stuff goes up the magnetic field and gets shot out. So the material starts off down here and then gets shot out with the magnetic field. And of course the magnetic field goes with it too. The magnetic field goes with the stuff. So we're creating and generating magnetic field here that's getting blown out. Does that make sense? Okay. Eddington. Okay. Eddington, accretion, and luminosity. So the gravitational pressure is gmm over r squared. So that's the force from gravity. And the pressure that, so I have, this is originally worked out for massive stars, but it's the same physics. So I have a black hole here, and I've got some, I got a proton here. And it's going to feel a force of gravity. So that it's got a mass here, the mass of the proton over r squared. That's going to go inwards, and it feels a photon pressure, which is equal to the cross section times the luminosity divided by the actual density of photons, 4 pi r squared. And there's a c in there for units. Does that make sense? So this is just saying, how likely am I to smash my photon into my proton? And how many photons do I get? So that's the total likely of smashing that proton, divided by how thin I've spread out my photons. So the photons spread out as they get further away from the star. So when I balance these two things, I get force of gravity. So the force of gravity for the thing to accrete has got to be larger than the force of radiation. So we just set these two things equal to each other, and the r's cancel out. That's one of the important bits about this, is the radius cancels out. So this is true regardless of where you are in the star. There's not like one radius where things get blown out and one radius where things get sucked in. If you're looking at winds, that's actually true. So there are weird stagnation points where things change direction and change sound speeds and stuff if you're looking at stuff blowing off. But with the photons, this is just true always. So when the force of gravity is larger than the force of radiation, then we have that gm, mass of the proton, over r squared has got to be larger than sigma t L over c times 4 pi, and that r squared goes away. So we have this relationship between luminosity and mass. So as long as accretion is happening, the radiation force has got to be less than the gravitational force. That means that the luminosity has got to be less than all of this, which is just what's ever left over. You just do a little algebra. 4 pi g c, mass of the proton, divided by the Thomson cross section. So the Thomson cross section is just the probability that a photon, if it comes in contact with an electron, is the probability that it's going to bounce off in an inelastic manner. Thomson scattering is inelastic. So the Eddington luminosity is 10 to the 38 ergs per second times the black hole mass in solar masses. The actual number doesn't matter so much. So from this we can get three different things. So we get a luminosity, we get a mass, and we get an accretion rate. So the luminosity is just this. This is the definition of the Eddington luminosity. It's a property that any star has. So any star has a luminosity that's based on its mass, that if it can shine bright enough, then it can push all the stuff out. If it can shine bright enough, it'll blow itself apart. So that's the Eddington luminosity. The Eddington mass, well, if I assume, so I got a black hole that I see. I got an AGN that I see. And it's got some radiation. Now, if I assume that that's maximal, then I can get a mass as well. So I can just say, okay, I see some luminosity. If we assume that it's at Eddington, then that gives me the mass of the black hole. That makes sense? So this is how most black holes are, the mass of most black holes are measured. If you see something that says billion solar mass black hole, they measured it using the Eddington luminosity. So the nice thing about this, so it's a limit. So if I give you the mass that I measured with the Eddington luminosity, what does that tell you about the mass, the actual mass of the black hole?
Gotta be less.
That's the question. Bigger or smaller? Is this an upper limit to the mass or a lower limit to the mass?
If it's not there yet, then the mass could be much more.
Yeah, what's the other knob that I have that can turn the luminosity down without turning the mass down?
Temperature.
Well, the temperature is set by the mass. It's this other weird thing, the accretion rate. If it's completely starved and there's no mass around for it to accrete, then it can be way bigger than its Eddington mass because it's not lighting up. It could light up, but it's not. So the light, so like Santiago said, is an upper limit to the luminosity and a lower limit to the mass. It's the best thing that we got for most of these objects, because most of these objects we don't have ways to measure the black hole, other ways to measure the black hole mass. That being said, it works actually pretty good. So there was a great paper that I found when I was starting to teach this. I was like, how bullshit is this? And it actually works out pretty well. So for all the black holes where they have independent measurements of the mass, they're all accreting a little bit below Eddington. And Eddington is really clearly a systematically upper limit. So nothing is really accreting above Eddington, which is a nice thing. That being said, so the other thing, so the Eddington mass is just invert that. So you just get 10 to the 7 solar masses times the luminosity in I think that's a solar luminosity. So this is the mass. The other thing you can do is get the accretion rate. So m dot is the accretion rate. This is the luminosity over c squared. So L is E m dot c squared. M dot is just how much I'm accreting. Epsilon is my efficiency. So that's how much of that mass energy am I turning into thermal energy. And we showed last time that we can turn a whole bunch of it into thermal energy from the gravity. So the gravity is kind of an arbitrarily deep well where you can really extract a whole buttload of energy. So we get some fraction of that. So that gives you an expression. So we just solve for the luminosity, or for the accretion rate. So that gives us an expression, L over epsilon c squared, which we can work out. We can relate this to the Eddington accretion on the previous page and get an expression for the Eddington accretion rate. So this is how fast does the mass need to be sucked down to be lighting up at Eddington. Does that make sense? So we got these three things. We got the luminosity, we got the total mass, we got the mass accretion rate that are all related to Eddington. So Eddington has one of each of these things. It's the same physics, it's just scattering, Thomson scattering of electrons off of protons as they're trying to fall into a gravitational object. The other thing we can do is we can get a time scale. M over m dot gives me a time. This is a true thing. Q over q dot gives you the time scale for q to get as big as q is. That makes sense? So m over m dot gives me the time scale for m to get this big. So we just do a little bit of algebra and you get that the evolution time is the fraction that you're accreting at Eddington. So this is how close to Eddington are you actually accreting, times 10 to the 8 years. 10 to the 8 years is a long time. So if I have a 10 to the 9 solar mass black hole in like not quite 10 to the 8 years, or a little bit more than 10 to the 8 years, this has to be feeding maximally the entire time, which doesn't make a lot of sense because they're episodic. So how this object got this big, so for instance this Mortlock quasar, the Mortlock quasar is a 10 to the 9 solar mass and it's only 700 million years old. That's a lie, it's not 700 million years old. That's where it is. It's younger than that by a lot because it didn't form at the Big Bang. Its age in history is 700 million years, so it's younger than that by a chunk. So how did this object get this big? We don't really know. So it's got to start off really big, but it's got to start off to make it work to be like 1,000 solar mass star. So that's weird.
Is it possible to have like multiple black holes just kind of
Merge?
Yeah. Just over and over again?
Yeah, each one of those has to accrete too. So I got to get all those guys bigger. But we clearly have a bunch of merging going on because we can see it now with LIGO. So we can see all these mergings. So maybe mergers. That's how it has to happen. But then how do you get two really big solar mass black holes next to each other? Weird questions. Hopefully there's going to be a homework problem on that. There isn't currently one. I got to write it. Okay, so getting mass from Eddington requires the assumption that the black hole is accreting maximally, and it gives a lower limit. Let's see, what else? Okay, so we found the temperature. Make sure you understand that derivation, not the GR parts, but the rest of it. So it's not super long. It is kind of ugly, but it's just a little bit of calculus and then some physics. So get your head around this T of R. It goes like radius to the 1/4. And then Eddington, the luminosity, the mass, and the accretion rate, all super important quantities. Okay, any other questions on that? I'm going to talk about spectra next. All right. Spectra. Oh, hey, there's a date here. I'm changing all that. That's wrong. I used to. So when I started writing all my slides for this, I would write the slide deck for the day. And then the next year I would have that slide deck, but it would be a different day and I taught different stuff, so I'd have to change it. But now I realize that I need to write a little thing for every day and then just write my lecture notes and not touch them. Works out a lot better. Anyway, so okay, pieces of AGN spectra. So let's actually so we're going to talk about the synchrotron emission, which is in the radio. We'll talk about the continuum emission, which is in the infrared, optical, and UV. We'll talk about broadline regions. We'll talk about broadline regions for a little bit because even though they're not a huge chunk of the picture, they're a really useful chunk of the picture. We'll talk about narrow line regions and we'll talk about X-rays. Yeah, that's it. So this is what our continuum looks like. So this is a spectra. This spectra goes from 1100 angstroms to 5000 angstroms, but the spectra above goes from several meters to how big is that, an X-ray? Yeah, an attometer, I think. Something really small. That's in frequency, so it's C over that. So we have this crazy amount of radiation. So the synchrotron, here's a couple of FR1 and FR2 radio galaxies. So the galaxy is here in the middle. So this is the galaxy right here, and these are blobs of stuff that come out of the side of the galaxy that you can't really see in the optical, but you can see them in the radio. And they are caused by this jet that's at the center. So the jet wraps up the magnetic field, makes a corkscrew. That corkscrew shoots stuff out. That stuff then mixes with the environment. Depending on how aggressively it's getting shot out, it'll mix more aggressively. So if the accretion rate is low, then you'll have something like this FR1, which is pretty compact. But if you have something where it's high, then you have an FR2, and the jet can go a lot further before it starts to entrain gas from the outer area. Entrainment is the word that's where you've got a jet of fluid. Other fluid near it is going to get sucked into that jet and move along with it. You can see this if you went to the physics open house. We had a demo where we had a hairdryer and ping pong balls, and you can float ping pong balls on the hairdryer using Bernoulli. It's a similar idea. Things get sucked into that jet because it's lower pressure. But then you're loading your jet, and it mixes the stuff with the intergalactic medium. So here, this guy gets to go pretty far before it starts to mix, and this one does not. So I'm not going to get too deep down this rabbit hole because you haven't had ENM yet, and you really need ENM to do synchrotron. But we'll get started. So given an electron with energy E equals gamma mc squared, what's gamma? What's that?
It's the power root minus b squared is c squared again.
Right, this is the Lorentz factor. That's right. Gamma is 1 over 1 minus v square root of that over c, or c is 1. So what does this thing do when v gets close to c? This blows up like, I mean, it blows up like a square root. It's not like an exponential explosion, but it still blows up, right? It gets really large when v gets close to c. So the energy goes like gamma mc squared, because that's what energy does when things get close to the speed of light, is it goes up. But you've got this Lorentz factor. You can kind of see this as masses go up as you get close to the speed of light. That's a fine way to think about it. The frequency of rotation is this. So you can sort out what the frequency of a thing going around a magnetic field is. Here, I'll show you real quick how to do that. F equals Q V over C cross B. Right? We've seen this before. This is the Lorentz force. So I can say mx double dot, that's a vector, equals Q over C V cross B. Let's say that B equals B naught in the x hat direction. So V cross B is what? The only way I know to take a cross product is using the triply antisymmetric tensor. I don't know if you've seen that before, but that's the way I know. That's the way I remember how to do it. So, do you see something stupid? Have you guys seen Einstein notation?
I think
Yeah.
we
just did it in class.
Oh, really? Okay, cool. So how do you take a dot product, A dot B, using Einstein notation?
Isn't it
Oh, really? That's awesome.
A sub I, B sub I?
A sub I, B sub J, sum for the
Yeah.
Well, I can do it that way. So how does this work? I sum over both sets of integers, right?
Mm-hmm.
Kronecker delta kills everything wherever I is not equal to j. So that's a fine way to do it. A cheaper way to do it is just say AI BI. That's it. I'm just summing over those things. How do I take a cross product using Einstein notation? If you just saw this, you haven't seen that yet. So I'll show you. You don't have to remember this. Epsilon I j k. This is the triply antisymmetric tensor. This is the Levi-Civitati. Oh, you did the so this is the Levi-Civitati, or the triply antisymmetric tensor. So IJK, if they're in order, it's 1. If they're not in order, it's -1. If anything is repeated, it's 0. Pretty simple. When I take a cross product, if I've got V cross B, this is epsilon I j k v j b k. You got this index salad. I j k. I is the index. So this is a vector, right? Cross product's a vector. So I is the free index. J and k get summed over. And when you do this, this is the same thing as when you make that little cross determinant and you do all the diagonal things. It's the same thing that you're doing. You're just writing out every possible combination of this, killing most of them, and adding a minus sign on half of them. So, back up here. Let's look at where the cyclotron frequency comes from. So I've got x double dot, and I've got x dot. Right, that's a vector. Let's actually call it v because it's easier. So v cross b is the I component is vj bi, and so for the 1 component, I got v2 b3 minus v3 b2. Because it's the 1 component, I got the triply antisymmetric tensor. The only thing that's going to show up is 2 and 3. So I got combinations of 2 and 3. One of them's got a minus sign and one of them's backwards. That's how you take a cross product. 2 is V3B1 minus V1B3, and 3 is V1B2 minus V2B1. Now, okay, B isn't just an X, so we get to keep this one, and that goes away, and that goes away, and that goes away. So now let's go back to F equals MA again. So M, let's put this M over here. Let's put all the constants over one side. So I have X double dot equals VZ times BX times Q over MC. No, that's Y double dot. And Z double dot is equal to what? The other direction, minus VY BX Q over MC. Okay, so now I've got, so this is Z dot, this is Y dot. Everybody good? I take a derivative of this guy and I stick it in here, and now here I'm gonna bail because watching the rest of it isn't interesting. So now I just cross multiply, differentiate, and then I'm left with Z double dot equals Z dot BX Q over MC, and I'm just left with with things that go in a circle. Okay. You don't need to know that for now. That's just where you get it. So V cross B, QV cross B. You don't need to remember any of that, but I wanted to at least put it in front of you. Because this cyclotron frequency, that's where this comes from. And you can see that I got a Q and a B and an M and a C, like I had, but it's relativistic, so we have this gamma squared, and there's a 4 pi that comes out of the relativistic assumption. So relativistic electrons orbit with this frequency. That frequency is proportional to the magnetic field. It's proportional to the energy of the electron. That gives you radio frequency photons. It can give you higher energy photons if you could really crank up the energy of the electrons. But in outer space, they only get up to radio energy. No, I'm sorry, that's a lie. They get up to infrared energy. Sorry, that's a total fib. So they can get pretty high, but they don't get into the X-rays unless you can't get X-ray synchrotron unless you really work at it. Oh man. So this is how you get it. So you start with this, you take some derivatives, and you're left with this frequency. Magnetic field accelerates particles, and the power that comes out in watts per second is going to be basically Q squared. What's A? Now I forget. Man. Oh, acceleration. This is the acceleration field. Thank you. For non-relativistic electrons. And there was more, but it fell off. I edited it out. So one of the problems with this is that I get some power that is an energy per time that's coming out of the synchrotron electrons. So I can sort out a time scale. If I want to know a time scale for how long all of that energy should disappear, that's just going to be the energy divided by the power. Right? If you do this, you get something like 100,000 years. What's wrong with that? Was that?
They've been a lot longer than
They're around a lot longer than this. So you got to have, the jet has to have some source of hot electrons in it. That's a whole, we don't understand that. We don't understand why the jets keep being so bright for so long, because they're radiating, so they ought to cool off, but they seem to go for a really long time. That's a slide that should have been there. So the radio lobes, radio is generally in, radio's all over the place, often in lobes, often close to the AGN. So there's lots of radio that radiates from the whole process. There's a jet the whole way, from real close down to way far out, there's radio. and it's all from these hot electrons. Okay, I'm gonna say something about this next bit. Well, I can cover this. So, okay, synchrotron. Okay, so now we'll talk about the continuum. So, okay, remember last time we derived the spectrum of the disk. We derived the temperature spectrum. We in there implicitly assumed that it was a black body. Turns out that if you go take the actual spectra from close into the black hole, you get something that looks like this. So this top curve here is the spectrum that you get. And you can understand it as a couple of parts. So you've got, in this model, they've broken the disk into 3 disks. There's an inner disk, a middle disk, and an outer disk. Those disks have 3 different temperatures. They give you 3 different black body curves. Why do they have 3 different temperatures? Because they're at different radii. And remember, we found that the temperature falls off like radius. So we have these 3 disks that may give us 3 black bodies that give us this huge blue bump of excess light. So this big blue bump is caused by the hot inner disk of the AGN, and it's the black body. In addition, you have some other physics going on, like Balmer continuum photons. I'm not going to worry too much about that. Gives you this bump here. The important bit is that the temperature goes like falls off with radius. It gets cooler, but near the black hole, it's really hot. So this is 10 to the 5 Kelvin, pretty hot, times the accretion rate, goes up with that, times the mass, times the radius. So these are hot things, and they give you black bodies. And that's really all I have to say about the inner disk, and I'm done talking for the day. Tomorrow we will finish up with the broadline regions. So broadlines are cool because you can do stuff with them, like listen to the acoustic ringing of the black hole. All right. Office hours tomorrow at 4. If you get stuck on stuff, you can feel free to email me questions. Like if you're like working on it tonight and you get stuck, you can email me and I'll try to get back to you soon. So.